let's move on. So now we say that let p0, p1 dot 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 p of r be points which are geometrically independent in some r dimensional space, and we are dealing with a real space. So to say that we are dealing with real space, what I actually mean is that we are restricting ourselves into the real space, the real m dimensional space, where m is equal or greater than r. Then any r simplex is written as follows. We denote the r simplex with sigma r, and this is written as some small x that belongs to Rm, where x itself is given by a summation that is a linear sum, some Ci Pi, which is equal or greater than 0, such that sum of the Ci's or the coefficients is equals to 1. So let's take a moment and try to understand what we are actually doing. So I have these Pi's, right? These are my points. What is this C? C is some real number, since we're restricting ourselves into the real space, real m-dimensional space. So what this statement over is saying, that you take the points, you take their linear sum in such a way that these coefficients Ci, they sum up to 1. Okay, this is how we are denoting the R simplex. Okay, so this R simplex, if you realize that this is actually a set. Okay, because x belongs to this way and this is the sum. So now this Ci needs some explanation, these coefficients need some explanation, and these Ci's are called barycentric coordinates. And I'll now explain what do I mean by a barycentric coordinate. I'll just try to give you a motivation that I'm not going to get into the very mathematical details, but rather physical motivation. So this is some remark about the barycentric coordinates. To understand what this barycentric coordinate means, what we can do is that we can try to draw an example that is familiar from our high school physics. Is that this is a coordinate system in which the location of a point is specified by reference to a simplex. Okay, this is more of a geometric definition, but we want to see a more physical example of this barycentric coordinate. And this physical example that relates this barycentric coordinate to the definition of the center of mass coordinates. So if you recall from physics, mechanics, high school mechanics, the center of mass, I'm writing it as COM, let's say you have some mass distribution like this, okay, and let's say this is at a location R1, this is R2, R3, R4, dot dot dot. Then the center of mass, let's say this is the center of mass, COM, denoted by capital R, is denoted by MR, where M is the summation of all these small masses, and this is M1R1. For our discussion, let's say all the M's are same, so this is R1 plus R2 plus R3 da 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 da, R of n, right? This is how we would compute the center of mass. So if you try to see here, is that this definition of the center of mass is almost similar to this summation over here, but the only constraint is that all the summation of these coefficients is equals to 1. Okay, so using the definition of center of mass as some analogy, we interpret the barycentric coordinates of a point is such that the masses, that means we started with some mass distribution, such that the masses are placed at the vertices of a simplex. Okay, and if you do that, then the summation condition that we saw earlier, this condition can be thought of, can be interpreted as a normalizing condition. What is normalization? Well, if you have let's say you are talking about probabilities, then you know that the sum of all probabilities is equals to 1. So that can be interpreted as a normalizing condition. This is just a constraint that you can put there. Okay, but all this is for your information only. It will not be very it will not concern us very much. So the takeaway is the definition of the simplex and how we can actually build these things up. And now we want to talk more about this some things that are associated with these simplices. So now we want to talk about the faces of a simplices, and we'll see that the idea of a face will actually get generalized. Okay,